Good afternoon, I am Eduarda, and I'm going to present programmable hash functions in the multilinear setting and show some cryptographic schemes that we can construct which are secure in the standard model. This is a joint work with Hofheinz, Kenneth, Paterson, and Christoph Striecks. So first of all, what are programmable hash functions, or PHFs for short? PHFs are group hash functions with some special properties for security proofs. And as the name says, it has some programmability properties. They were originally proposed by Hofheinz and Kenneth in 2008. Actually not proposed, formalized. Basically, a PHF can behave in two indistinguishable ways. First, if a standard key generation algorithm is used, then a key for the hash function is produced, and then the hash function normally hashes its input into a group element. However, if a trapdoor key generation algorithm is used, then a key together with a trapdoor is generated. And the trapdoor will allow us to program the hash function so that the output of the hash function has this special form shown in the yellow box, where C and H are elements from the target group, and the exponents AX and BX depend on the input X. You can imagine that C is our challenge element, and then the output of the PHF will have a challenge element only if AX is different from 0. And this is going to be very useful for security proofs because it allows us to partition the input space into two disjoint sets. The set where we can handle adversarial queries, and the set where we can embed a challenge element. So we say that a PHF is mn programmable if for m values xi and n values zj, we have that the ax are equal to 0 and the az's are different from 0 with some noticeable probability. Currently, we have many constructions for PHFs. We have one poly PHF, where poly here means that the programmability for the second element holds for every polynomial Q. Actually, this kind of PHF was implicitly used in Waters' paper from 2005 in his IBE scheme and signature scheme. And we also have M1 PHFs, but here for a fixed M. So how about poly 1 PHFs or poly n PHFs? Well, it would be very useful to have them. But do they exist? Well, in Crypto last year, Hanoaka et al. Showed that it's actually not possible to construct such hash functions, such programmable hash functions. So in our work, we are going to construct analogs of poly n PHFs by adapting the original PHF definition. And we call them poly n m PHFs. And we work in a setting where multilinear maps are available. So with our MPHFs constructions, we are able to construct standard model versions of the Bonnet-Franklin IBE scheme of the...
Use this one instead.
It's not working?
Yeah, so they can hear you better.
Okay. Of the BLS signatures and of the Sakai Yogishin Kasahara HIDNIKE scheme. And as Kenneth said already, the BLS, our standard model version, is going to be identity-based. For those of you who are not familiar with the term HIDNIKE stands for Identity-Based Non-Interactive Key Exchange. Like in IBE, we have a trusted authority who generates private key for users. But here the goal is that any two users can use their private key and together with their identity to non-interactively compute a shared key. And not only that, but we also have hierarchical versions of all these schemes in the identity-based setting and with security in the standard model. I would like to point out here that our HIDNIKE scheme is the first one which achieves security in the standard model. The only efficient HIDNIKE scheme that existed before our work was the one by Sakai Yogishin Kasahara, but which has security only in the random oracle model. Also, our hierarchical HIDNIKE scheme is the first one which is fully secure with security either in the standard model or in the random oracle model. And I'll explain later what I mean by fully secure. And in this talk, I'm going to focus on our hierarchical HIDNIKE construction. In our paper, we use a proper abstraction of the GGH candidate for multilinear maps, but I will leave this out of the talk for simplicity, and I'm going to use ideal multilinear maps. So this is our abstraction for multilinear maps. It's the same that Susan explained before. We have an L group system, groups G1 up to GL, all of order P, and we have a collection of maps, of bilinear maps EIJ. A map EIJ is going to map an element from group GI and an element of group GJ to an element of group GI plus J. And also for simplicity, we're going to drop the indices I and J, and instead of using EIJ, we use only E. So we can see that this actually can be seen as multilinear maps. And for security of our constructions, we have two hardness assumptions. We use the L plus 1 power assumption, where we have G and G to the X from the group G1, and we have to distinguish this S, this element S in the topmost group from a random element. In the paper, we also use this LMDDH assumption, but I will not need it for this talk. So here's our definition for MPHFs. The algorithms are very similar to the algorithms for PHF, but the key difference here is that in order to program the output of the PHF, instead of using elements C and H from the target group, we are going to use a number of elements from the group G1. These are the elements C1 up to CL and the element H. Also, the AX and the BX here, they play the same role as in the PHFs. But notice here that the BX, instead of being an exponent, is a group element from GL minus 1. And as for PHFs, we also have the same programmability properties. That is for M elements X1 up to XM, and for N elements Z1 up to Zn, we have that the probability that the AXs are different, the AXs are equal to 0, and the AZs are different from 0 with some noticeable probability. So let me show our construction. First, I will show our construction for poly 1 MPHF into GL. And as an ingredient, we use an admissible hash function from K bits to L bits. The key for our MPHF consists of 2L group elements, where these elements are from G1. And in order to, the output of our MPHF is going to be the multilinear map computation of L of those elements. And in order to choose these L elements, this is going to depend on the output of the admissible hash function on input X. This is actually what will enable us to achieve adaptive security in our proofs. So an admissible hash function is basically a special type of hash function that has certain combinatorial properties, and they can be constructed, for example, from codes. And so we use these properties to prove that our construction is actually a poly 1 MPHF. So now that we have a poly 1 MPHF, we can also construct a poly N MPHF. And this is basically a product construction where the output of the poly N MPHF is the product of the output of N instantiations of a poly 1 MPHF. So before I explain how our HIDNIKE scheme works, I would like to first formalize what is a HIDNIKE scheme. So like in hierarchical IBE, we have a hierarchy of depth L, and every node in the hierarchy is represented by a vector of identities. A HIDNIKE scheme has 3 algorithms: a setup algorithm, a delegation algorithm del, and a shared key algorithm SHK. So first, the TA is going to run the setup algorithm on input a security parameter and the depth of the hierarchy to generate a master public key and a master secret key. Then the TA is going to use the delegation algorithm to generate private keys for all its children. And then any identity in the level 1 of the hierarchy can use its private key to generate private keys for all its children, and it can do this by using the delegation algorithm. And the process continues until we reach the bottom of the hierarchy. Now, any 2 users in the hierarchy should be able to compute a shared key using the shared key algorithm, and they can do this non-interactively. For this, a user uses its private key and the identity of the other element, and together with the master public key to generate a value. Of course, when the other identity does the same procedure, it can obtain the same value. In this example, I show that 2 users in the bottom of the hierarchy can non-interactively compute a shared key, but the HIDNIKE scheme is not limited to that. As I said before, any 2 users in the hierarchy should be able to compute a paired key, a shared key. For security, we consider an indistinguishability-based security model where an adversary can learn private keys for an arbitrary number of users and can also obtain shared key between pairs of users, and has to distinguish between the shared key of a pair of users of its choice and a random element. And security in this sense is what we call full security. I didn't mention that, of course, we have to avoid some restrictions. We have to consider some restrictions to avoid trivial wins. And before I move on to explain our HIDNIKE scheme, I would like to mention that there is previous work on this primitive. There is a scheme by Gennaro et al. However, that scheme has some drawbacks. At the higher levels in the hierarchy, only a limited number of nodes can be compromised, as opposed to an arbitrary number. Security is only achieved in the random oracle model, and the shared keys can only be computed between leaf nodes, that is, between nodes in the bottom of the hierarchy. So this is our HIDNIKE scheme. The main idea here is that the TA is going to generate L instances of PHF, and 1 for each level of the hierarchy. And it's going to use this as part of the master public key. There is also another very important element that it uses in the master public key, which is a random element from the group GL, where GL is the target group for the PHF. This is the element U, and I'm going to explain later the importance of this element. So now, the private key for a user in the first level of the hierarchy is going to be the hash of that identity raised to the power x. And notice that here we use the first instance of our PHF because the identity is in level 1. Now the private key for a user in the second level of the hierarchy is going to be the multilinear map computation of the hash of that identity and of the hash of its ancestor. And all this raised to the power x. And notice that because the ID now is in level 2, then we're going to use the second instance of the PHF to hash that identity. And in general, inside the multilinear map, we are going to use the hash of the identity along with the hash of all the ancestors of the identity in order to compute the private key. And of course, we have a proper delegation algorithm so that any user can use its private key in order to generate private key to all its children. Now, the shared key between two users at the bottom of the hierarchy is going to be the multilinear map computation of the hash of those identities, the hashes of those identities, along with the hashes of all its ancestors. And all these raised to the power x. It is very important to notice that this shared key has to be in the topmost group for some security reasons. So for example, if one of the identities is not in the bottom of the hierarchy, then we are going to use that U element that I mentioned before in order to complement that multilinear map computation so that we reach the last level. And this is our main theorem. If our MPHF is a poly 2 MPHF into GL, then our scheme is secure under a proper power assumption. That this will depend on the level of the hierarchy. And before I finish my talk, I just would like to mention that we can generalize our HIDNIKE scheme and our hierarchical HIDNIKE scheme to a setting where with multiple TAs. So we have, for example, that if two users get private keys from possibly independent TAs, they can still compute a shared key without any interaction. And we can also generalize our schemes so that it works in a setting where multiple identities can compute a shared key instead of only two. And as I said before, with our MPHFs, we can also construct IBE schemes, hierarchical IBE schemes, signature schemes, and hierarchical signature schemes. And our signature schemes are standard model versions of the BLS signature schemes in the identity-based and also hierarchical versions of that. And this concludes my talk. Thank you very much for your attention.